All right, good afternoon, everybody. I'm Jay Parlar, and today I'm going to be talking to you about finding bugs without running or even looking at your code. Now, this talk is from the general class of things called formal methods. There is a Slack channel, formal methods, if you want to join, talk to other like-minded folks. So this is a pretty big claim I'm making here, and you'd be fairly reasonable to say impossible, right? How can we possibly find bugs without looking at the code or even running the code? Well, what are a few ways that we find bugs right now? There's at least a couple we can all probably think of off the top of our heads. Reviewing PRs, right? Awesome way to find bugs. In fact, it's one of the best ways to find bugs. Testing, manual and automated testing, you're definitely going to find bugs like that. Static analyzers, really cool tools that can analyze your code base, find bugs that humans often can't find. The problem with all of these and other methods, though, is that they all require that either you or a tool is looking at your code or that your code is running in the case of testing. And I'm not interested in any of that for today. So what then is my secret solution to finding bugs without running or looking at code? It's this: talking to an expert and writing stuff down. You just start there, and you're going to be in a great place. Now, who could this expert be? This could be the architects or the developers or the technical documentation writers, anyone that has a really solid understanding of the system being described. But how do you actually find code or find bugs by talking to someone? Well, I want you to think back to situations you might have been in the past, I certainly have, where you are explaining a system or an algorithm or a problem you've got to someone else, or maybe they're explaining something like that to you. And in the process of describing this algorithm, system, or problem, the explainer stops, they get that wonderful look on their face, and they go, aha, I figured it out. I just realized my problem, or I just realized a bug I never thought of before. All right, there's something about the process of explaining things to people that seems to cause our brain to work in a different way and explore paths of execution for your system that you might not otherwise have considered. Now, this could be because the listener asks a very astute question at the right time. That definitely happens. But for me, I've had a lot of instances where the listener doesn't say a word, and I still have that aha moment. And in fact, you don't even have to have a listener. The simple process of writing down on paper what you know about a system or what you think you know about a system will often clarify your thinking in a way you might not otherwise have done and cause bugs to be exposed. Now, this is a favorite quote of mine. Writing is nature's way of letting you know how sloppy your thinking is. It's a popular quote in formal methods circles. And the reason for this is what I was just saying, that simple process of putting pen to paper and describing your system clarifies our thinking and in an often unexpected way leads us to think about our systems in a different way than normal. So looking at the clock here, we're 3 minutes into the talk, and there's a couple things you're probably thinking to yourselves at this point. One might be, how should we write down our thoughts or designs or plans or strategies around a system? Great question. Another question you might be asking, did I really come to a talk about bug discovery where the solution is go talk to people and write stuff down? Both very valid questions. I'll tackle that first one first. So there's lots of ways you can write things down. Informal natural language descriptions, UML diagrams, pseudocode, state machine descriptions, sequence diagrams, whatever you want. Just, it's important that you're taking a different approach to your system. You're writing it down in something that is not code. You're letting your brain think at a more abstract level than the code. Now, a way I like to write stuff down is to use something a little bit more formal than natural language descriptions. I like to describe my systems in a way that not only does it help my thinking, but a computer can understand my thinking. And in doing this, I can leverage the massive brute force power of modern computers to not only help me have more of those aha moments, But so sometimes the computer can have those aha moments all on its own. And fortunately for everybody in the audience, I think, the way I like to do that also answers the second question. I'm not just going to stand here and say, talk to people and write stuff down. That is an excellent strategy. And if you only take one thing away from the talk today, let it be that. Write more things down. It will clarify your thinking, and it'll cause you to find bugs. But that's not going to be the focus today. Today, I'm going to talk about this. It's a tool called Alloy from MIT. Unfortunately, the font sizes on the buttons are not configurable, so I'll just have to tell you what they mean later on. Alloy comes from the general class of tools called model checkers. And if you're not familiar with a model checker, what they are is they're a system that lets you describe your code, describe your design in a formal way, such that your computer, leveraging that massive brute force power we now all have in our laptops, your computer can use that formal design to explore the entire sequence, or every single sequence of operations your program might ever enter, every single state your program might ever enter. And while doing that, it can check that certain correctness properties are always holding. And if the model checker finds any state in which a correctness property fails, it'll tell you right away, and it'll say, hey, you've got a bug there. All right, so in other words, we're using model checkers to help our thought process. All right, we're leveraging this massive brute force power of computers to explore a little. So before I actually open the real tool, that's just a screenshot, let me describe the example I'm going to build up in the tool. So this is a very simple example of a permissions system. It's going to have three kinds of things in it: accounts, resources, and users. And that's it. Resources and users are going to belong to accounts. Users potentially have the ability to access a resource. Think of that like the user has permission on the resource, or the user has a role into the resource. Resources can optionally have a parent resource. And why would we want to do that? Well, the reason is that in this permission system, we want to say if a user has access to a parent resource, then they implicitly get access to all of that parent's children. Okay? So that's the example we're going to build up. I bet a lot of you could take these 5 points here, go write some code, and build a great system around this. But I'm not that smart, so I need to write things down. So let's take a look at Alloy and see what this looks like. OK, so what we have here is that same Alloy tool. I've fed in a little bit of the design. So you can see right now we have three things. We have accounts, users, and resources. You can think of the word sig kind of like class or typedef, something along those lines. So right now we're telling Alloy the system we want to design is going to have accounts, users, and resources in it. Great. What can we do with this at this point? Well, there's a lightning bolt icon here that says execute, which may or may not be readable on the projector. I'm going to click that, and instantly, within a millisecond, Alloy says instance found. Now, what does that mean, instance found? Well, let's click it and take a look. So what we have here is a valid instance of this system based on the description I've given Alloy thus far. Alloy has said, OK, we can have users and resources and accounts. Here's a valid instance of your system in which 2 accounts have been instantiated. Great. Not super interesting, but it's always neat to see diagrams coming out of a programming tool. Now, there's another button here in the visualizer called Next, and I'm going to click that. And what Alloy is going to do is generate a completely different valid instance of this system. So this instance has 2 accounts and 1 user. No resources still, but this is just the instance Alloy decided to generate this time. I'll click Next once more. Here we go. 2 accounts, 1 resource, 1 user. So we can look at this, and as programmers, we can say, well, the system we talked about had resources and users belonging to accounts. Nothing in this diagram shows anything belonging to anything. There's no hierarchy here. There's no structure here. That's because we haven't told Alloy about any structure. So let's go back in and add a little bit of structure to our design. I'm not brave enough to type things out live, so I've got different files here where just pretend I instantly typed it out perfectly every time. So now you can see I've added some attributes to these classes or to these SIGs. And think of it like object-oriented programming. We're adding attributes to an object type. So the account SIG, or the account class, now has a resources attribute. And that resources attribute is going to point to 0 or more resources. In other words, these are the resources that belong to the account. The account SIG also has a users attribute, which points to 0 or more users. In other words, these are the users that are going to belong to a given account. The user object or type itself also has a resources attribute, but here, this is going to represent the set of 0 or more resources that the user has permission to access. And finally, on the resource, we have a parent attribute. And remember, we said a resource can optionally have a parent. So that means it can have 0 parents or 1 parent. And that's what the lone keyword does. It means less than or equal to 1. So every resource is going to have less than or equal to 1 parent resource. OK, so that's maybe a little bit interesting. Let's click execute, start generating fresh instances, fresh possible scenarios the system could enter, and take a look. So this diagram looks a lot more interesting than what we just saw, right? There's actual structure here. In this particular instance Alloy generated, it has said, OK, given the description you've given me, here's an instance with 2 accounts, 1 resource, or 2 resources, and 1 user. We can see that resource 1 belongs to account 0. Resource 0 belongs to account 1. And our user belongs to both accounts. Now, I don't know if you've ever done anything in the realm of security, but you probably don't want a user belonging to 2 separate customer accounts. Sometimes you do. In this case, we don't. So what Alloy has done here, just by showing us a possible instance of our system, it's illustrated a problem to us. I just had an aha moment. I realized that my design is not precise enough. I haven't actually specified in my formal design that every user can only belong to 1 account. So how are we going to do that? Type really fast. I added this thing here called a fact. A fact is a constraint that we place on the system. Alloy will only generate instances now that satisfy this constraint. And what does this fact say? It says that for every user, U, there's going to be exactly 1 account A for which U belongs to account A. All right? In other words, a user can only belong to 1 account. Now, when I click execute, Alloy is going to generate fresh instances again. And you can see, in this particular instance, we now have the user just belonging to 1 account. I could click next probably 10,000 times. Every one of those 10,000 times, it's going to show me a different scenario. And in every single one of those scenarios, each user will only belong to 1 account. So great, we're doing better. But I see more problems here. I'm having more of these aha moments. In this particular instance, resource 0 belongs to account 1. That's fine. Resource 1 belongs to account 0. That's also fine. But there's a parent-child relationship between those 2 resources. From a security perspective, you probably don't want that as well. If customer 0 owns this thing and customer 1 owns this thing, you probably don't want a link between those 2 things. So again, we haven't been precise enough in our specification. We didn't think about possible scenarios. So let's fix that. Type. I've added another fact here. All the facts must be true all the time, so our previous fact is still there. But I've added another fact that says for each resource R, if the resource has a parent, because remember we said it's optional for a resource to have a parent, but if a resource has a parent, it implies there's going to be exactly 1 account for which R belongs to that account and which for R's parent belongs to that account. In other words, if a resource has a parent, they're both going to belong to the same account. So let's execute, see if we're now happy with the diagrams we're getting. So that's a little better. Resources are in the same account. But again, I'm seeing another problem. Maybe you see it here. Resource 1 has itself as a parent. That seems weird. I probably don't want to allow that in my system. I don't even know what that would mean. Again, maybe some systems that's what you want, but for the system we're designing, I don't want that. So let's fix that. We're going to add another fact, another constraint. And this fact says that there shall be no resource R for which R is its own parent, or R is not in its own chain of parents. Don't worry too much if you don't understand that. I can talk to you about it later. Well, click execute. Take a look at the instances. All right, so here's a fresh instance. Not too interesting, but I don't see any problems here. Another one, no one is its own parent anymore. That's pretty good. Users are all doing the right things. This looks pretty good. And I could go through for a while here. I normally wouldn't, but I can go through for a while and just stop when I'm happy. But I'm not happy because I just came to a diagram where something else weird is happening. This user that belongs to account 1 has permissions on resources from account 0. We probably don't want that either. You don't want users from one customer account getting roles on something from another customer account. So Alloy, again, has given me one of these aha moments, something I didn't think about that we need to fix. So that's what this fact here does. This is saying for every possible combination of user and account, if the user is in that account, it implies that all of the user's resources, or all the resources the user has permission to, are also in that account. And now when I execute, generate instances, I can click next forever, and we're not going to see any of those problems. So let's go back to the Alloy for a moment here. What we've been doing thus far is having Alloy generate instances, and we've been pretty lucky in that right away we found problems almost every time. That's great, and oftentimes you will find problems almost right away. But what if there's something in particular we want to check for? We want to see if something is possible. I don't want to click next 10,000 times. That's ridiculous. So what Alloy has is the concept of invariants, or assertions, if you like. And I'm going to add an assertion in here. And an assertion you use with the check keyword. And an assertion is a belief you have about the system that we want Alloy to check for us. So it is my belief that for every single resource, there's always going to be exactly one account that the resource belongs to. Now, this is kind of a made-up example because I know it's not the case. And I think if you've been thinking through this, you might realize we haven't actually said that a resource can only belong to one account. So obviously, Alloy is going to find a problem here. So I'm going to ask Alloy to check this for me. And if there's a problem in which my belief is not true, it'll show it to me. So I'm expecting to see a diagram in which a resource belongs to two different accounts. Right? I think that makes a lot of sense. So this time I have to use the drop-down menu here, but I'll click check. And it says counterexample found. So Alloy found a scenario in which my belief is incorrect. So we're probably going to click this, and we're going to see a resource belonging to two accounts. We don't, though. And I honestly never thought of this the first time I put this presentation together. Here's a resource that belongs to no accounts. The belief we had was that, the way we wrote it, is that every resource is going to belong to exactly one account. Our implicit notion there was, well, because we don't want a resource belonging to two accounts. But what Alloy said was, well, here's a case where a resource doesn't belong to one account. It doesn't belong to any accounts, and we probably don't want that either. So let's put a little fix in for that. We're going to add a new fact. Don't worry too much about the syntax of this one, but it's saying that it's basically forcing every resource to belong to an account. So now let's check this check this property again. We're going to get a counterexample more like what we expected. Here's one in which there's a resource that belongs to two separate accounts, all right, which is what we thought we would see. So now we can fix that particular scenario. I'm going to add a little bit more to the fact here. And this is saying there shall be no two accounts such that those accounts share any resources. That's another way of saying a resource can't belong to two accounts simultaneously. Now when I check, we're good. It says no counterexample found. Now one last thing I want to do in Alloy is I said that if a user has access to a parent resource, they should implicitly get access to all of the parent's children. Okay? And now we can start to model some of the logic we might use in our actual code when we go to implement this in Python or Java or Go or whatever you like. And so we're going to have this predicate, which is a function that returns true or false. And this is the logic I decide to use to model whether or not a user can access a resource. So this function is going to take a U and an R, which are a user and a resource, and it will return true if the resource is in the set of resources the user has permission on, Or it'll return true if the resource has a parent, and that parent is in the set of resources the user has permission on. Okay, so this is the logic we would potentially use in our software to actually check whether someone should be allowed to access a given resource. And now, just because I wrote this logic down doesn't mean I've actually done everything correctly. So we want to have another check. We want to declare another property that we believe to be true, but we want Alloy to check for us. And this is saying that I believe that for every possible combination of user and resource, if the user can access the resource, then it implies that the user can access all of the children of the resource. Okay? And if you're not following 100%, I know this is new to probably 99% of you. Don't worry. I'm just trying to give you a taste of it. So let's do this check here, see what Alloy says about our belief. Instantly, Alloy says, counterexample found. I have found a situation in which your belief is not true, which is legitimately surprising because I thought that this can access was OK. So let's look at the counterexample. Now, because of the resolution, I have to scroll a little bit. But what it's saying here is that resource 0 is in the set of resources that user 1 has direct permission on. Okay? And resource 0 is the parent of resource 1. And user 1 gets permission to access resource 1 through that parent-child relationship. But here's the problem. User 1 has access to resource 1 through that parent-child relationship, but they don't have access to resource 2. And that's what I intended. If there's any parent-child relationship, it should go all the way down from the top parent to the bottom child in that chain. And given what we've declared here, the user would not actually have access to this resource. Okay? So I'm not going to fix this today, but I just want to give you a taste of what it's like to check these properties in Alloy. And sometimes the surprising, well, oftentimes the surprising results that you're going to have. So what did we actually do in this nice little Alloy example? Well, we did what I call two things. We did a design validation at the end. The validation is where I was declaring properties I believed to be true, and Alloy was checking whether or not those properties actually were true. And this is an incredibly powerful aspect of model checkers, and it is one of the biggest reasons people use them, and it's an amazing reason to use them. The model checker has an ability to check properties that we just can't write unit tests for. It's too hard to come up with all the possible permutations of unit tests. Model checkers are incredible at this. But think back to the beginning of that Alloy example. What was I doing there? We didn't have any checks until the end. I was just generating diagrams. And what was that process? That process was design exploration. Okay, it's one thing to write a property that you believe to be true when you're deep into the system and you know what you believe to be true. But what about when you're just starting out on a new system, or you're trying to understand a system that's been presented to you? You don't even know what you don't know, right? So what Alloy does is it gives us a way to explore possible scenarios that your systems might enter, and then you can look at those scenarios and decide whether they make sense or not and whether you have to do something about it. So that was a pretty trivial example. I'm now going to talk about real-life uses I've had of Alloy. And the first one, I was at a previous company, and I was helping model the interaction between multiple systems in Alloy. Why would we want to do that? We wanted to do it for experimentation purposes. They were proposing adding a new feature to a very core system, and we wanted to see how other systems might be able to leverage that core feature. And it's a lot easier to experiment with 300 lines of Alloy than it is with hundreds of thousands of lines of Java and Python across multiple code bases deployed to AWS or wherever, and complicated development environments. I'll take the Alloy any day for experimentation. So what systems did I model in the Alloy model? Well, I modeled multiple customer portals. This company had a few different customer-facing product portals. I modeled the notion of browser sessions, of an identity provider, the notion of auth tokens, and for this particular company, they actually had an old style token and a new style token, and depending which portal you were in, it changed the kind of token you needed. I modeled the notion of SAML requests and responses. If you're not familiar with SAML, it's the way that a lot of companies do logins for their websites, and more. And I didn't just model those systems from a static view. I actually modeled operations that could take place between the systems. So the operation of a user choosing to navigate between portals. The operation of portals initiating SAML flows. They're going to take some time The notion of an identity provider responding to the SAML flows. The notion of the identity provider redirecting to a credentials page for users that haven't logged in yet. The notion of a user entering either good credentials or bad credentials or wrong credentials. And you'll see soon what I mean by wrong. And more. So I modeled a lot of stuff. Now, one of the things I did while modeling these systems was I wrote this property here. And we don't just write properties so Alloy can check them for us. We also write them so other readers of the spec can get a sense of what we believe to be true. All right, so it's really useful documentation. And what does this particular property say? It says that there shall be no point in time t in which one of our customer portals has an auth token for a user, but that same auth token is unknown to our identity provider. If that actually happens, it's a security flaw. Because if an auth token gets out there to a customer portal, and then the identity provider loses track of that auth token, it means the identity provider can no longer revoke that token. And there's an innumerable number of ways in which you have security flaws if you can't revoke someone's token. All right, both good reasons and bad reasons. So I wrote this property not expecting to find any problems, but then I clicked execute in Alloy. Counterexample found. Assertion is invalid. What happened? I was very surprised by this. So what Alloy did was it generated a sequence of 13 operations that, if they happened in this particular order, would cause this security flaw. Now, I'm not going to show you the way Alloy drew that. It's a little bit easier. I put together my own little animation to help describe the sequence of operations that Alloy discovered. I did not tell Alloy to run these 13 steps. Alloy figured it out on its own. So here's what the scenario Alloy discovered that leads to a security flaw. User visits the new portal. So this customer, again, had a new product portal and an old portal. The user visits the new portal. The portal says, I don't know who you are. I don't have a session for you. You need to log in. The portal generates a SAML request. Portal then redirects the user's browser over to the identity provider. Identity provider says, great, I love SAML requests, but I don't have a token for this user yet. I need to send the user off to the credentials page. Browser gets redirected to the credentials page. At this point, though, we have our first mistake. The user, instead of entering credentials for the new portal, they enter credentials for the old portal, because this user happens to have multiple accounts with the company. Okay, with different sets of credentials for the different accounts. So they enter old portal credentials, old portal creds 1. The login page sends those off to the identity provider. The identity provider says, great, credentials. I'm going to generate a token from those. But because they're old credentials, or old portal credentials, an old style token is generated. The identity provider then has to throw away the SAML request because it can't send an old token to the new portal. So it holds on to the token, throws away the SAML request, immediately redirects the user's browser to the old portal. User lands at the old portal. The old portal immediately says, I don't have a session for you. Off to the identity provider you go, with a SAML request in tow. The identity provider says, great, I've got a SAML request. I love SAML requests. This one is from the old portal. Even better, I have an old style token for the old portal. So I'm going to generate a SAML response, send that back to the old portal. The old portal says, great, I love SAML responses. Consumes the token in the response, holds onto it, now has a session for the user, and the user's confused. Because the user meant to log into the new portal like 2 minutes ago when I started this. And there's just been like automatic browser redirects the whole time. The user's like, well, something went wrong. I meant to go to the new portal, so I'm just going to click my bookmark for the new portal, go back there. New portal sees the browser. Browser says, I don't know who you are. I'm going to generate a SAML request. Sends the user over to the identity provider. Identity provider says, great, I love SAML requests. This is a SAML request from the new portal. I don't have a new token. Got to send you to the credentials page. User goes down to their credentials page. The user makes another mistake. They don't enter those old portal creds that they entered last time. They don't enter their new portal creds. They enter a different set of old portal credentials because they have 2 different accounts. The login page sends the user back to the identity provider, and here is where the bug was that Alloy found. What the identity provider was doing was saying, great, credentials, I'm going to generate a token. But note what happens here. Because it's a different set of credentials, a different token gets generated. Now we have old portal token 2 in the identity provider. We now have a live token out at a customer portal that our identity provider doesn't know about. That is what we call a security flaw. We can't revoke that token anymore. Okay, so this was scary to me when I saw it, because I must have done something wrong. And I thought I did something wrong because I never looked at a single line of anybody's code to generate the model for that. All right, I had a 300-line Alloy model that was encompassing the actions of 5 or 6 different code bases. I knew roughly what those code bases did, and I had talked to their developers a little bit, but I never looked at any of their code. So I assumed I had made a mistake in the model, but then when I presented the results to the developers, they said, yeah, we have to delay our release on Friday because we need to go fix this problem. And I also want to stress again that I didn't tell Alloy, here's a ridiculous sequence of 13 steps. What happens? Alloy figured it out on its own. It figured out that if these particular 13 steps were to happen, we would get a flaw. So that was one fun experience I had at a previous company with Alloy. Here's another one. So the company this time had been working on a brand new API for a year. They'd put a ton of effort into it. And very shortly, 5 or 6 different systems around the company were going to start consuming this API. And I was brought in to help have the first system integrate with the API. Great, no problem there. The issue was the API was actually kind of hard to understand. Through no fault of the API itself, but it was modeling a lot of pretty intense, or it had a lot of pretty intense business logic behind the scenes. And you couldn't really understand how to use the API unless you understood the business logic. So what did I do to help myself understand the business logic? I decided to write an Alloy model. Not to prove anything wrong or prove anything right, but remember what I said before, writing things down helps you think better. Alloy helps me think better. And what did this process look like? So that's me on the left. I'm Jay, again. The developer I spent most of the time talking to, his name is Bob. Great guy. So I took the documentation for the API, and I built an initial Alloy model. And while trying to build that model, I realized there was gaps in the documentation. Because I had to write the Alloy piece, and there was no corresponding documentation to tell me what to do. So I'd go to Bob, and I'd say, hey, how does ABC work? What do I do here? And he would always give me an incredibly detailed, very well thought out answer. Awesome. So that would give me more information to build out my model. So I'd go, iterate, 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 work on it for a little bit. Then I would start to generate some instances. Once I had the model at a reasonable enough spot, and actually I had the model at a reasonable enough spot to generate instances on the first day, but what I'd start to do is I'd see these kinds of scenarios like we were looking at before, things that looked off to me. Like I thought, maybe that shouldn't be possible. And I'd say to Bob, hey, is this allowed? Like this diagram here, could your system actually do that? And sometimes he'd say, nope, nope, you've made a mistake in your model. And sometimes he'd say, yeah, we actually can do that. You've got your model right. And so based on these answers, I could refine the model, iterate, iterate, iterate. I then added the notion of operations, these sequences of over time to the model. And I'd say, hey, Bob, could this particular sequence of operations ever take place? And oftentimes, especially at that point, he would say, I don't know. I have to go look at the code because that's a complex sequence and it'd be bad if that happens. So I really hope we have code to account for that. And every single time he came back and said, you've done the model correct and we're actually okay, or your model has a mistake, we have code that's going to prevent that bad situation from ever happening. All right, so he'd respond back. And after, like 2 weeks worth of minimal interactions, I was doing a lot of other stuff, but just sort of doing this on the side with Bob, working on building this model. And after about the 2 weeks, I realized something. I realized that the API that they'd spent a year on won't work. The API itself was technically brilliant and did exactly what it was originally intended to do. The problem was the user experience folks that had designed the customer experience had a completely incorrect understanding of what the API was capable of. And the API itself was originally designed for something different. And no one was able to understand the customer experience side and the API side. I came in already understanding the customer experience side. Alloy gave me the tools to build a mental model of the API side, and I realized, uh-oh, we can't actually do this. This is a problem. So they had to throw away a year's worth of work, which is never great, but it's better to throw away a year's worth of work than have 6 teams do an additional 6 months of work trying to integrate with an API that we're never going to be able to use. So those are 2 of sort of many personal examples I have with Alloy. I've got just enough time to show this because I love this. This is a this is a paper, or a result from a paper by Pamela Zave. And what Pamela Zave had decided to do was analyze the Chord protocol. And if you're not familiar with the Chord protocol, it's a distributed hash table. It won the 2011 SIGCOMM Test of Time Award for what a great algorithm it was. And the original paper presenting the Chord protocol is one of the most cited papers in all of computer science. Pretty good paper. Within the paper, the authors had 7 different correctness claims about the protocol. Our protocol will always do this. Our protocol will always do this. And they had mathematical proofs for all 7 claims. So what did Pamela Zave decide to do? Well, she decided to model with Alloy, as I said. And she turned each of those 7 claims into checks, the invariants, the properties we looked at before. And what do you think happened with each and every one of those 7 claims? Alloy found a counterexample. So for every single one of those claims the authors had made about this in this incredibly influential paper, every one of those claims was actually wrong. Again, Pamela Zave on her own didn't initially figure that out. Alloy showed her that these were wrong. She was then able to use Alloy to fix the protocol and show that the correctness claims were then correct. But it's just a story I love because there was this great thing that everybody adored, and Alloy said, no. Okay, so what are the takeaways? As I'm wrapping up here, what are the takeaways I want you all to leave with? First, write things down. If you never think about Alloy again when you leave this room, that's fine. But spend more time writing things down. Whether you're starting a project, whether you're trying to understand a project, whether you're trying to understand an algorithm, write it down in something other than code. Give your brain a chance to think about the problem in a different way, hopefully in a more abstract way, because code is not abstract at all. I don't care how many abstraction layers you have. Code is not abstract. Code is so detailed. The next part I want to talk about, or the next takeaway, is model existing systems. If you spend enough time in formal methods land, in a model checker land, people like to make a lot of claims about the power of using tools like Alloy for greenfield applications. Use Alloy to create the blueprints for your system, and then use those blueprints to easily write the code after. That can happen. It's cool when it happens. But realistically, how often are we working on greenfield projects? I'd say that as an industry, most of our time is spent maintaining existing projects or adding features to existing projects or jumping into existing projects you don't previously have experience with. Modeling those projects, those systems, has enormous benefit, not just for finding bugs like Alloy did, but for you and your ability to learn the system in a different way. It's helped me immeasurably over the years. And then finally, do that thing I was just talking about, model new systems. If you're working on something green, try using a modeling language. Oftentimes, you're going to be able to find really deep, subtle problems at the modeling stage when all you've done is a couple hundred lines of Alloy code. And it's better to find it at that stage than when you're about to go to production and you realize a bug that requires you to change everything. Right? You definitely don't want that. So a few resources I'll leave you with so we can get these on the slide for people to check out later. So alloytools.org, and specifically /book.html. For better or for worse, the Alloy book is amazing. It's written by Daniel Jackson, the author of Alloy. It is the way almost everybody learns Alloy. There's very few other resources because the book is so good. No one else bothered to spend time doing anything else. The Architecture of Open Source Applications book is free online. There is an Alloy chapter in it, which is just lovely. A fantastic, fantastic chapter showing how they model browser sessions and cores and security flaws around all of that stuff. I'm going to call out my friend Hillel Wayne. Some of you may know him. He helped me put together the accounts users resources example I had. He was a big part of the inspiration for that. Not only is he an expert on Alloy and loves Alloy, he is also an expert on TLA Plus and loves TLA Plus. And if this stuff seems interesting to you, he does really fantastic corporate workshops, so hire him. I get $0 out of that, but he's just a fantastic person, and your company will be in better shape if you hire him to do this. What is TLA Plus? TLA Plus is another modeling language like Alloy. It does some things better than Alloy. It does some things not as well as Alloy, but there's an incredible amount of resources out there on TLA Plus. We had a pre-conference yesterday that was all TLA Plus. And if TLA Plus interests you, a really quick way to get into it is the website learntla.com, which also happens to be a Hillel Wayne joint, so check that out. And there's multiple formal methods people here at Strange Loop this week. Find us in the Slack channel, find me, I can point out friendly faces. And that's it. Thank you very much.